Welcome. This question says a 3.6 kilogram block has a gravitational potential energy of minus 43.7 joules. When located in space near planet Zebron, what is the magnitude of the gravitational potential, Vg, at that point in space? So here's my visualization. I have my planet, I have my block, and this block has a certain potential energy by virtue of its position within the gravitational field created by planet Zebron. And okay, I've been given the gravitational potential energy, but I want the gravitational potential. And the gravitational potential is, if you like, the gravitational potential energy per unit mass. It's joules per kilogram. It's analogous to, in the past we talked about the gravitational force, and then we talked about the force per unit mass, which was the gravitational field strength, and then we started talking about the gravitational potential energy, and now we're talking about the gravitational potential energy per unit mass, joules per kilogram. So it's analogous, just like gravitational field was a bit abstract but very useful because you can put any mass you like at a position, and if you know the gravitational field you can figure out what the weight would be. So the gravitational potential is very useful because if you know the gravitational potential you can put any mass you like at that point and you will know its gravitational potential energy. And so I keep this in my mind. I also kind of, in brackets, I have my delta UG, because we very often talk about the difference in gravitational potential energy. And we also talk about my delta VG because we talk about our difference in gravitational potential. Gravitational potential would be very analogous to electric potential, which is really commonly used when we deal with electric circuits. So I'd like to encourage you to get comfortable with this idea of, in this case, energy per kilogram, because in physics 2 you will be talking about energy per charge. So I'd like to introduce it a little bit in physics 1 so that it's not such a shock in physics 2 when we use electric potential all the time. It's a very useful concept. We don't tend to practice it much in physics 1 because we tend not to hop from planet to planet to planet in physics 1. And it's a pity, really. It's a pity that we do not travel so much, because in physics 2, we hop from charge center to charge center to charge center all the time. So with that said, what I can say is, oh, well, let's visualize. Here's my planet Zebron. I have no idea what the mass of it is. I have no idea how far I am away. All I know is that this little block has a UG of equals minus 43.7 joules, and I know it has a mass is equal to 3.6 kilograms. And so I can say, well, just like I said that G is equal to Fg over m, I can say, in this case, let's do it in a different color, I can say that Vg is equal to Ug over m. It's by analogy. So I can say, well, my Vg, my gravitational potential, is equal to my gravitational potential energy over my mass, which would be 3.6, which when I work it out is going to be, let's do this, 43.7 divided by 3.6 is equal to, this equals 12.2 joules per kilogram. joules per kilogram. It asks me for what is the magnitude, so I can say, well, okay, Vg magnitude is equal to 12.2 joules per kilogram. So there we have it. It's a bit of an unusual concept. It is sometimes skipped over because it kind of comes at the end of a sequence for gravitational potential energy and gravitational force and gravitational field. And the reason why I include it is because when we get to physics 2, we'll deal with electrical potential energy, electric force, electric field, and we will deal with electric potential to a great extent. So a little bit of forewarning here. So there we have it.